Hi, good morning to everyone. Welcome to my channel Elecom Edu. Today the topic is binary codes. We already know what is binary. What is a binary? It is a combination of zeros and ones. Now we will see how the binary codes are getting executed. Binary codes. See, it is representing the information in the language of digital system. That is the binary codes. You already know the machine can able to communicate by the language as a combinations of zeros and ones. So check over here. I have given 10110. It is a sort of information passing from machine to machine. What are all the binary codes? The binary codes are BCD, XS3, gray code, ASCII and parity. BCD, that is a binary coded decimal. Next it is a XS3. So the value will be exceeded 3. Next it is a gray code, changing only one bit by the sort of the another value. Next it is a ASCII. So you can able to code all the numericals, spaces, special words, keywords, everything to some other binary values. Next it is a parity. If any error has happened, we can able to detect and correct the error. This is a simple explanation for the codes. So after end of this session, you will able to answer all these questions. Why binary codes? What are the classifications of the codes? What is meant by BCD and XS3? What is gray code? What is the error detection and error correction codes? What is meant by cyclic codes, CRC? What is meant by Hamming code and what are the applications of ASCII? The first one, motivation of this topic. Why do we need a binary codes? You already know the digital circuits can able to understand only two voltage states, high and low. I mean bit 0 as well as bit 1. Bit 0 is the lowest value and bit 1 is the highest value. So binary code is a set of rules that map each symbol of information. See, in the example I have given, the decimal digit as 7. For this decimal digit, I am going to apply the encoding rule BCD. What is BCD? It is a binary coded decimal. So from that itself, you can understand the decimal number is going to be coded in terms of binary. You already know 8421 code. So here you are going to apply that concept 8421 code. This decimal digit may be a letter or it may be an instruction also. And what is the 8421 code for 7? It is 0111. So that is what I represented there. So binary code is a set rule that maps each digit of information, or it may be a letter or instruction, onto unique group of bits. So any real world data can move through purely two state hardware, bit 0 or bit 1. So every binary code is simply a mapping table. The design choices are which bit pattern represents which symbol and why. And what are the advantages of this binary code? First is hardware simplicity, because only two-state logic gates are enough to execute this. It is a cheap, fast and reliable build. Next one, it is a data integrity. What is the data integrity? Structured codes let the circuit detect or correct transmission errors. Next, it is interoperability. There are some standard codes like ASCII, BCD and all. Let the devices exchange the data predictability. The next motivation of this is classification. The families of binary codes are classified into two ways. One is a weighted code and another one it is a non-weighted code. In the earlier classes we discussed weighted code. What is a weighted code? So each and every position is having some values. There you have to consider both the place value as well as a phase value. So what is a place value? The position weight. What is a phase value? Whatever numerical you can able to see visually. So each bit position carries a fixed positional value. That is your weighted code. What is a non-weighted code? There is no fixed or numeric weights for any bit position. So the examples of weighted code, that is a standard code already you know, that is 8421 code. This 8421 code is not only using for hexadecimal conversion, we are also using it as a standard binary coded decimal BCD. Next is 2421 code. Next it is 5211 code. If you consider the non-weighted codes, XS3, gray code and ASCII. ASCII is nothing, it is a character code. First we will see the weighted code. What is the first weighted code? 8421 code. Already I introduced you this in the hexadecimal conversion. So this 8421 code is a standard BCD, binary coded decimal. You already know the decimal values are, the Unix symbol for decimal values are available from 0 to 9. So each digit should be encoded independently. So how we are encoding? We are encoding based on the weights as 8421. So check over this tabular column, whatever I have given here, 8421. So how many decimal digits are there? 0 to 9. So for decimal 0, 8421 code is 0000, means that no position is having a weights. Next it is 1. Only weight is applicable for the first position. That's why it is 0001. Next it is 2. 0010. 2 alone is having a weight. Next it is 3. 2 plus 1 is 3. So 2 and 1 is having a weight on, other places or weight off. Next it is 4. 4 alone weight on. So 0100. Next 5. When you will get 5? 4 plus 1 is 5. So 4 and 1 weight on, other two places are weight off. Next it is 6. So 4 plus 2 is 6. So 4 and 2 weight on, other places are weight off. 7. 4 plus 2 plus 1 weight. 7 weights on, other places weight off. 8. 8 alone weight on, other places weight off. 9. 8 plus 1 9. So 8 and 1 weights on, other places are weights off. So for a BCD, remember it uses only 10 of the 16 possible weights. You already know 8421 code, it is from 0 to 15. So after 9, you have to represent a 10 as A, 11 as B, 12 as C, 13 as D, 14 as E and 15 as F. But for binary coded decimal, that 10 to 15, A to F is not applicable. Those are invalid and unused codes. The applicable or allowed values are from 0 to 9. That is 0000 to 1001. Next it is the non-weighted code. What is that non-weighted code? 3 codes I introduced you. One is the XS3, another one it is a gray code, next it is a ASCII code. We will see one by one. So the first code it is a XS3. So from that word itself you can understand XS3. So means that each value is going to exceed 3 times. That's it. So what you have to do? You have to add 3 to the decimal digit. Then convert the result to 4-bit binary. What is that 4-bit binary? Standard 8421 code. That's it. Okay. One more thing I want to tell you here. This XS3 code is also termed as a self-complementing code. So the self-complementing code, it is actually used for BCD subtraction, not a ones complement or twos complement. I am mentioning here it as a BCD subtraction. We will see what are those things. So first check that excess 3. What is excess 3? Decimal value should be added with 3. After that, what you have to do in the second step, you have to convert it into 4-bit binary 8421. Check over that tabulation, whatever I have given. The digit is 0. Binary, decimal digit is 0. So to that decimal digit, you are going to add 3. What is 0 plus 3? 3. So what is the excess 3? 8421. What is that 8421? 0011. Take the next example, 3. Your decimal digit is 3. You have to add 3 with that. So 3 plus 3, it is 6. So what is your excess 3? 0110. Next it is 7. So 7 plus 3, 10. What is the 10 in your 4-bit binary? 1010. Last value I have given it as a 9. Digit is 9. Decimal digit 9. 9 plus 3, 12. So how to convert it into the BCD standard? 1100. This is the way how the excess 3 is performing. So excess 3, which is actually using for the BCD subtraction. Okay. Check over what is the self-complementing property. Right. See, in the self-complementing property, take that example. What is your actual digit, decimal digit? It is 3. Right. You have to convert it into excess 3. So if you are converting into excess 3, what will be the result? 3 plus 3, it is 6. So 0110, right? Here, this is nothing. It is a 9th complement of the digit, right? So for that, first what you have to do? First you have to convert this 0110 to ones complement. What is a 0110's ones complement? You already know what is ones complement. 0 should be complement to 1 and 1 should be complement to 0. So 0110 will become 1001. So what is 1001? It is a 9th complement of the 3. Right? What is that 1001? It is a 9th complement of 3. Right? So this self-complementing property is nothing. It is a 9th complement of the digit is obtained directly by inverting every bit of its excess 3 code. No extra logic is needed. So 0110 is converting to 1001, which is a ones complement of the excess 3. The next one, it is a gray code. Remember, gray code is also a non-weighted code. So means that there is no need for any positional weight or is no need for any position where the bit is available. So the gray code, what is the gray code? Only one bit changes at a time. That is a gray code, right? Okay. The other name of the gray code is reflected binary code, right? Between any two consecutive values, exactly one bit should be flipped, right? Other bits and all should be available as such. What is the advantage of this? This actually minimizes the switching error. Maybe in the mechanical encoder or it may be in the rotatory encoder. For example, you are passing some information, okay? I am passing the information as 101, right? So from my side, I am passing 101. But while receiving, it is received as 001. So what is happening there? One bit is actually flipped. Why that flipping is happened? Because of the error, transmitting error. Okay, right. So check over this table. In the first row, I have given the decimal values 0, 1, 2, 3, 4, 5, 6 and 7. In the second row, I have given the binary. Till 7 it is there. Then what code is this? Try to recollect. What is that code? Yes, exactly. It is 4 to 1 code you have used in your octal number system. Okay. So the binary values are for 0, 4 to 1. All weights are 0. For 5, 4 plus 1 is 5. So 4 and 1 is switched on, other values are switched off. That's why you got it as 101. So 7. When will you get the 7? 4 plus 2 plus 1, 7. So all the weights should be switched on. So the second row, which is your 4 to 1 code. Third row, it is a gray code. Already what I said, the gray code, when comparing two consecutive values, only one bit should be changed. So check your decimal 0, the binary value 000 and the gray code is 001. Check over your second value. When compared with the gray code of first decimal to the second decimal, what is happening? 001. Check, only LSB is flipped. In the third value, what is your third value? Decimal 2. In the decimal 2, what is the result you got? 011. Check here. MSB 0 is transferred as such. LSB 1 is also transferred as such. But what is happening to your mid? 0 is flipped to 1. That's why gray code actually only one bit is changing at the time. How we are getting these values? We are getting these values the way MSB should be written as such. MSB to the next position should be XORed. Okay, right? I will take 5 as an example. Okay, right. So what is the value for 5? 101. Yes, what is the value for 5? 101. How you are getting that 101? Because of that 4 to 1 code. What I said, the MSB should be taken as such. So what is the MSB there in your 5? 1. So next, MSB should be XORed with your next value. What is your MSB value? 1. What is your next value? 0. So what is 1 XOR 0? The value which is 1. So 1 should be written as such, right? Okay. What is the next representation? What is your next consecutive bit? 0. What is a LSB? 1. So 0 and 1 should be XORed. What is 0 XOR 1? 1. So the way how the binary is getting converted into gray code. Okay. So only one bit flips between the neighboring values. Where we are using this? We are using this in your SHAFT encoders, Karna map. So while taking a Karna map, I will explain you low power counters as well as error minimizing ADC. ADC is nothing which is an analog to digital converters. Okay, so we will see one example here for the conversion from binary to gray code. Okay, what is a binary to gray code conversion? Remember, MSB of gray code which is equals to MSB of binary code. Already I told this, right? In the earlier example itself I told MSB of gray code which is equals to the binary code. Okay. Each next gray bit is nothing which is a XOR of current and previous binary. So check the binary input whatever I have given. 1011, right? So check your left hand side. The left hand side is your MSB. Already you know. Check your right hand side. Right hand side is your LSB. What is there in your MSB? 1. How I said? The gray output and the binary input should be similar in the MSB position. So whatever 1 represented there, it is taken as such. Next, what you have to do? The current bit. What is your current bit? 0 is your current bit. What is your previous bit? 1. So 1 and 0 should be XORed. What is 1 and 0 XOR? The value is 1. That should be placed in the next position. Okay. Now what is your current bit? 1. What is your previous bit? 0. So you have to XOR 0 and 1. What is 0 and 1 XOR? 1. Now what is your current bit? 1. What is your previous bit? 1. XOR 1 and 1, the value is 0. So the binary input is 0011, but the gray input is 1110. Check. wherever the values are changed, how many bits are changed? Only one bit will be changed from one position to the another position. Okay, right. So this is a binary to gray code conversion. Next, we will check how to do the gray conversion to binary conversion. See, for binary to gray conversion, you have to use XOR gate. The gray to binary conversion, for a gray to binary conversion, you have to use a XOR gate. Okay, right? Everywhere you have to use only the XOR gate, right? Okay. So what is a gray value I have given? 1110, right? Always remember the rule number 1 is MSB of binary, which is equals to MSB of gray. So I have taken as such. So gray input is 1, binary output is also 1. Next, what you have to do? Current value should be XORed with the earlier value, right? What is your current value? 1. What is your earlier previous value? 1. What is 1 XOR 1? It is 0, right? So next, what you have to do? 1 XOR 1. What is 1 XOR 1? It is 1. So the last one is 0 XOR 1. That is also 1. So what is the value? 1011. This is the way how you have to convert the gray to binary representation. The next one, it is a error detection. Okay, right. Error detection, it is a parity bit. Remember, if you want to detect any errors, you have to use a parity bit. Parity bit is nothing, it is a extra bit getting appended or added to the data word. After doing that, you have to check whether it is a even parity or odd parity. If the total count of 1 matches a chosen rule, we may say that the bit is no error. If any mismatches happened at the receiver signal, we used to call some error is happening there in the particular transmission. Okay, right. So what is a even parity? The total number of ones must be equals to the even value. That is a even parity. What is an odd parity? The total number of ones available in the bit is an odd number. That is an odd parity. So check the even parity. What is the data I am going to send? 1011, right? So I am adding one parity bit. So what is the parity bit I am adding? 1, right? So what is a parity bit I am adding? I am adding a parity bit 1. So check over your next representation. It is an odd parity. So in the odd parity, I want to send it as an odd parity. So when I can able to send it as an odd parity? Whenever the number of ones are odd, right? So the number of ones are odd, it is a 3 ones. So that's why it is an odd parity. But here the number of ones are even. That's why it is a even parity. Okay. Check here. How many ones are here? My message is having 3 ones and I have add one parity. So 3 plus 1, 4 ones. So 4 ones means it is a even parity. Check in the odd parity. My message is having only 3 ones. Means it is an odd parity. So I want to send it as an odd parity. That's why I have given my parity bit as a 0, right? So if it is an even parity, number of ones are even. If it is an odd parity, the number of ones are odd. So what are the limitations here? It can able to find only 1 bit error. That is a limitation for the parity bit. But even it can able to detect the transmission error. It can't able to find which position is having the error, but it can able to find it is having a error. Next, error can be controlled. How can you able to control the error? By detecting the error as well as by correcting the error, right? What is meant by detecting the error? You can find whether error is there or not. So that is a deduction. So something went wrong. That is a deduction, right? What is meant by correction? Where the error is happened and where the bit is getting flipped, that is termed as a correction. But no retransmission is needed. Okay. So deduction means only flags that something went wrong. Correction means which bit is wrong and flips it back. Okay. Right. So check, I have given two datas there. Okay. What is my first code? 1010. What is my second code? 1001. Check from the MSB. MSB of both the codes are same value, 11. The next position, both the codes are same value, 00. The next position, 10. So one bit is changed. In the next position, I mean in your LSB, again 01. One value is changed. So means that two positions getting changed. LSB, that is 2 power 0, which is changed, as well as 2 power 1 is also changed. So how many positions changed? 2 positions changed. So means that Hamming distance is equals to 2. So Hamming distance is nothing, number of bit position in which two codes differ. That is a Hamming distance. Okay. So if you are following a Hamming distance, you need to follow some rules for that. Okay. To detect the error as well as correct the error. Right. The general formula to detect the error is t plus 1. The general formula to correct the error is 2t plus 1. Okay. Right. Check the minimum distance needed. Detect one error. What is the formula I said? T plus 1. Please stop the video, write down this equation. Okay. So for detecting the error, the equation is t plus 1. So t is equals to 1. So what is t plus 1? I mean 1 plus 1, the value is equals to 2. So what is the equation or value to detect the one error? Greater than or equals to 2. How to correct the error or what is the equation to correct the error? Stop the video. Please write down this equation. It is 2t plus 1 greater than or equals to 2t plus 1. What is t here? 1. So 2 into 1, 2. So 2 plus 1, it is 3. So for correct the error, greater than or equals to 3. So everywhere if you want, you can check over. For detect two errors, you need t plus 1. So 2 plus 1, it is 3. Detect correct one as well as detect 2. So there also you can find the value based on the equation, whatever I said. So what is the redundancy rule you have to use here? Remember, the redundancy rule, you have to use two values. One value is a message bit and another one value is a parity bit. So message bit, I am representing by the letter M data bits, and the parity I am representing by the letter R. So what is the formula I followed there? 2 power R greater than or equals to M plus R plus 1. So this is the way you have to apply the redundancy rule, right? Okay. I hope till this it is clear for you. So next one, it is a cyclic code. So cyclic code, we used to call it as a CRC. So what is a cyclic code? Cyclic code is a linear block code. So this linear block code with some defining property, right? So any cyclic shift of a valid code itself is a valid code. Here, check over, I have given you three representation. One is a message M of x. Next one, it is a generator G of x. Next, I have given the reminder is equals to CRC bits. So how to generate the code word, transmitted code word? Message bits plus CRC reminder appended before sending. Before sending, you have to follow this part. Okay. What are the advantages of this cyclic code? It is a powerful burst error detection. The second one, it is a simple shift register hardware. The third one, everywhere in networking, we are using only the CRC code. For example, in the Ethernet frame, whenever you are using that zip files or PNG files, I mean for images, disk storage, all uses actually CRC only, right? In the shift registers, it is also using a division by g of x. What is that g of x? Generator implemented with XOR gates and shift register. Okay. Right. So next it is a Hamming code. Alright. In the Hamming code, check the title what I mentioned. Hamming code encoding 7, 4. There you are seeing two values, right? 7, 4, right? So the 4 represents the data. The 7 represents the total bit. So how many parity bit you have to use? Total bit minus the message bit. So total bit is 7, message bit is 4. So 7 minus 4, 3. That is what I mentioned down. Okay. So 7 is a code word. For that 7-bit code word, what do you have to do? For 7-bit code word, what we have to use? We have to use 4 data bit plus 3 parity bit. Okay. So 4 data bit plus 3 parity bit is equals to 7-bit code word. Okay. Right. So what is my message now? What is my data bit? 1011 is my data bit. Okay. But how many code words? How many bits there in my code words? 7. So how many parity I have to add? 3 parity I have to add. We will see those things and all. Remember, parity bit can sit only in these particular position. Position 1, position 2 as well as position 4. Remember, okay? Parity bit should able to sit only in these position. So check here. Parity 1 I represented in position 1. Green color I mentioned. Parity 2 in position 2. And parity 4 is my parity bit. Okay. Other bits are my data. Right. Okay. You have to find what values you have to place there in the position 1, position 2 as well as position 4. Right. P1. So how to calculate the value for P1? D1 XOR with D2 XOR with D4. That is the formula. What is for P2? That is D1 XOR with D3 XOR with D4. What is P4? D2 XOR with D3 XOR with D4. Right? You already know D1. What is your D1? 1. D2 0. D3 1 as well as D4 1. So check D1, D2 and D4. 1 XOR 0 XOR 1. So 1 XOR 0 is 0. 0 XOR 1 is 0. Because in XOR code 0 0 0 1 1 0 1 1. Okay. What is 0 0? 0. 0 1 1. 1 0 1. 1 1 0. So 1 0 1. Right? 1 0 XOR is 1. 1 XOR 1 is 0. So next check your P2. 1 XOR 1 XOR 1. So 1 XOR 1 it is 0. 0 XOR 1 which is 1. So what is for P4? 0 1 1. Please write down these things and all and calculate and understand. So what is 0 XOR 1? 1. 1 XOR 1, 0. Right? So you have found the value for parity 1, parity 2 and parity 4. Where should be the parity 1? In the first position, 0. Parity 2, second position, 1. Next is your data, 1. Again, that is your fourth position. You have to make your parity 4. What is your parity 4? 0. So the remaining all are the values whatever in your data. So 0, 1, 1, 0, 0, 1, 1. So this is your Hamming code encoding representation. See, now you have forwarded the values, right? You have sent the values. What is the value you have sent? 0, 1, 1, 0, 0, 1, 1. Please check the slide. In the sent, I represented 0, 1, 1, 0, 0, 1, 1. Okay. But while receiving, how it is received? 0, 1, 1, 0, 1, 1, 1. So means that See, from the MSB, please calculate. MSB is your first position. 1, 2, 3, 4, 5. In the fifth position, the bit is flipped because what we are sending 0, but what we received 1, right? So now what we have to do? We have to check where the error is produced, right? Where the error is available, right? So for that, what you have to do? You have to check, right? Okay. So for checking, again, check C1, C2 and C4, right? What is the syndrome there? It is C1, C2 and C4 because what is the parity you used? P1, P2 and P4. So here also you have to do that same, right? C1, C2 and C4. Okay. We will see what is happening. How to find the C1? Position 1, 3, 5, 7 should be XORed. How to find C2? Position 2, 3, 6, 7 should be XORed. How to find C4? Position 4, 5, 6, 7 should be XORed. Okay. So position in the sense you have to check the values whatever available there. What is the value available there in your position 1? What is the position 1? 0. What is your position 2? 1. Position 3? 1. What is your position 7? 1. So 1, 3, 5, 7. So 1, 3, 5, 7 is 0, XOR with 1, XOR with 1 as well as XOR with 1. What is the value you got? 1. So 0 XOR 1. Again remembering 0, 0, 0, 1, 1, 0, 1, 1. So 0, 1 and 1, 0 is 1. So 0 XOR 1 is 1. 1 XOR 1 is 0. 0 XOR 1 is 1. Right? So in the value it is 1. So next check here 1, 1, 1, 1. So what is 1, 1, 1, 1? It is absolutely 0 because 1, 1 is also always 0 only. Right? As well as 0, 0 is also 0 only. In the last position also it is getting mismatched. Right? So how to write the syndrome? C1, C2 and C4. What is C1? 1. C2, 0. C4, 1. So 1, 0, 1, it is 5. So means that fifth position is error. Okay. So flip it back and read the value as 0, 0, 1, 1, which is the recovered value. This is how we have to find and fix the error by using the Hamming code. So next it is the ASCII code. ASCII means it is the American Standard Code for Information Interchange, right? In this one, every letter, whatever you are visibly, whatever you are seeing and visibly there in your keyboard, it may be the letter, it may be the digit, it may be the symbol, right? Everything which is actually patterned as a unique 7-bit binary, right? I mean 128 codes are there. One more ASCII is there. We used to call it as a extended ASCII. That extended ASCII uses 8 bits. Okay. For example, I have given only some 2 or 3 values. See, uppercase A. What is the uppercase A? The decimal 65. You already know how to make that. 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5 and 2 power 6. Okay. Right. So what is 2 power 5? 32. 2 power 6? 64. So 64 plus 1, 65. That's why other values and all weight 0. Only these two values are weight 1. See, next I have written it as a small case, right? Lower case. Lower case, the decimal is 97, right? Next I have given the value 0. 0 means it is a numerical. Next see, I have given you the special character, exclamatory. Next I have given the space. So each and every character which is coded as a 7-bit binary. That is the ASCII representation, right? Based on this, how to encode the word hi? It is having 2 numericals as two digits it is having, right? One is a H, one alphabet, and another one it is a I, one more alphabet. So for H, the H alphabet, which is coded as a 7-bit binary pattern as 100100. I 10010001. So the high should be written in binary as 1001001001. So this is a ASCII coding, right? So by this class, on this session, what you learned? You learned weighted code as well as non-weighted code. In the weighted code, what you learned? 8421 BCD, right? How many bits are there? 4 bits are there. What is happening here? The direct decimal digit is getting mapped to 8421. Next, it is the XS3 and gray code. Both are the non-weighted code. So XS3 also it is having a 4 bits, because that also follows only 8421 code. But what is happening? Each decimal digit is getting exceeded by 3 values. That's it. So what is the advantage there? It is a self-complementing. So the next one, it is a gray code. Gray code is a kind of non-weighted code, but what is happening there? Only one bit is changing between the consequent values, right? Okay. The bits, there is no limitation. It is a n bit. Next, it is a parity code. Why we are using a parity code? To detect the error, right? Okay. So for parity code, what you are using? You are adding or appending one bit to your message bit, right? So plus one is getting added. While doing that, if the number of ones are even, we used to call it as a even parity. If it is the number of ones are odd, we used to call it as a odd parity. So flags, odd count bit error. Next, it is a cyclic CRC. That is also used to detect the error. How many is getting added? Plus R is getting added. So catches burst error via the polynomial division. Next, it is a Hamming code. Hamming code is a error correcting code, right? I have given you the example for 7,4. I mean a plus 3. P1, P2 and P4 parity bit locates and fixes a single flipped bit. Last one, which is a ASCII. ASCII means it is a character code. Like all the digits, all the alphabets, all the special characters which are patterning as a 7-bit binary. If it is an extended ASCII, it is an 8-bit binary. So the advantage is encodes letters as well as the symbols. Where these binary codes are shown up in your calculators as well as the displays. You used to see that 7-segment displays, right? So those are actually BCD only. That is happening because of the BCD drive. Next, it is a rotary and shaft encoder. Particularly the gray codes are using. Next, it is a serial data link because of parity bits we are using. Keyboards and text storage, ASCII, already I told. Whatever you can see there in the keyboard, everything is getting converted to the 7-bit binary pattern in the ASCII. Next, it is digital arithmetic unit. So XS3 are using there because BCD subtraction via 9th complement logic. Last one, it is a memory addressing. So these are the place or applications where the binary codes comes into the picture. So by this class, what you learned? Binary code. So binary code is a design choice. It may be the weighted code or it may be the non-weighted code. Error may be available or error may not be available. Anyhow, the system needs to match all these parts. Okay. Thank you so much for watching this session. And if you have any questions or any queries, any doubts, please post in the comment box. You will get the reply soon. Thank you so much.